Now that we have stress intensification factor completed and we understand that concept, we need to move to a more central and somewhat more complex concept called displacement, stresses, and strains. This part of this video deals with just that. We know that whenever there is a displacement in any member, there is always an associated stress. That relationship between the stress and the strain can be shown on a stress-strain diagram. As we know, the units on strain are length per length, which might be inch per inch or millimeter per millimeter. And the units on stress could be PSI or maybe megapascals. If the material is linear in stress versus strain, as most steels are, we can take the slope of this linear line. That slope is Young's modulus. If the behavior of the steel is considered to be elastic, no plastic, then the stress-strain line goes and continues past the yield point as shown. Thus, when the elastic stress principle is used, any stress that is calculated beyond the actual yield stress point is not representative of the stress in the pipe. ASME B31.3 is an elastic stress code. Per B31.3, the allowable stress at room temperature is usually 2/3 yield. It can be 0.9 times yield, but specifically for this discussion, we'll use the 2/3 yield. For temperatures exceeding room temperature, it's 2/3 yields times a temperature reduction factor. Now let's discuss displacement, strain, and stress. As discussed, whenever there is a displacement in any material, there is an associated stress, as referenced with, again, our stress-strain curve. Now, as we have studied in the last tech talk, secondary or self-limiting stresses, the code, ASME code, both pressure vessel and piping, allow for the stresses to exceed the yield, since again they are self-limiting. Once we finish this section and understand displacement stresses, we will look in detail at how ASME B31.3 sets the allowable stress for any strain, displacement strain. Now let's look at the relationship between stress and strain for a material undergoing sustained stress, which must be under the allowable or 2/3 yield. So as we progress with increasing strain, we see that the stress follows the Young's modulus stress line. The strain cannot produce a stress greater than 2/3 yield for sustain. Sustained stress, again, being pressure or weight. Next, from the 2/3 yield point on the stress-strain line, we go straight down to where we will find the actual strain that caused the 2/3 yield stress, which is the maximum strain allowable. If now the piping system were unloaded, then the stress would go back to zero, and we have now a cycle that can occur and is fully code compliant. This is the maximum strain/stress cycle that can occur for sustained stress. There are no thermal strains occurring for this cycle we have just seen. Next, we turn our focus to secondary or self-limiting displacement stress. We have stated that the code, specifically B31.3, allows secondary or self-limiting stress to exceed allowable indeed to even go into yield. It can actually go up to 2 times calculated yield, as shown in the figure. One immediately thinks that because we are going to 2 times calculated yield, that the strain within the metal itself would be very significant. Now going down vertical, we can see how much strain was involved in the actual steel. Even though there was double the yield stress calculated, the actual stress in the steel did not increase very much at all. That's because it is self-limiting. Now, if the load for this self-limiting case were removed, then it would repeat and follow the same curve right back near to zero, just like the sustained case. In other words, what's important here is that even though there may be a very small unrecoverable deformation, the stress-strain cycle for self-limiting or secondary will be very similar in its recovery capability as sustained. The primary characteristic of the secondary stress is that it will go only so far and stop. Temperatures will reach equilibrium and the stress state will stop increasing. In this case, it must be below 2 times yield stress. So in summary, we see there are 2 kinds of displacement stresses. One is sustained and the other is self-limiting or secondary. We've also seen that both the sustained and the self-limiting displacement stress loops or cycles are both repeatable from load to no load states. With this repeatability comes confidence in operation and safety. Thus, the use by B31.3 of these constraints for both sustained and secondary stress displacements. Although there are times when we can use 2 times the yield stress for B31.3, paragraph 302.3.5 is the methodology where actual allowables for both sustained and secondary stresses are developed, and we go over that in this video. Twice yield, as shown in this example with the stress-strain curve, was for illustrating displacement stresses and strains only. So far we have looked at primary stress displacement and also secondary stress displacement from thermal, but there are other secondary or self-limiting stresses that the code calls out. We'll look at those now. From paragraph 319.2.1, we see that there are displacement strains other than thermal that are secondary. A is the thermal displacements, which we have just spent time with on the stress-strain curve. B is restraint flexibility, which means that if the strains are not rigid, you can take credit for their flexibility. The one we're interested in is C. Specifically, we're interested in externally induced displacements, such as tidal changes for docks or loading stations, wind sway for very high towers, and obviously, and one very common, is temperature changes in equipment, vessels, that we are attaching piping systems to. Clearly, all of these externally imposed displacements are self-limiting and must be handled exactly as the thermal stresses are being handled in our just discussed displacement stresses and strain methodology, i.e., that stresses and strains above yield are allowed. A very common movement for our subject matter experts is earth settlement. This occurs in places where there are very heavy weights, like for instance tank farms, very heavy modules, and also large diameter piping. This section states that the general paragraph 302.3.5 methodology for allowable stress can be exceeded if additional consideration is given for factors such as buckling and high localized stress. We now understand the technical stress-strain consideration for secondary and primary stresses from the stress-strain curve. Since thermal strains occur from one temperature to another, there is by definition a range of displacements that occur from one temperature to the other. We now move to look at how ASME B31.3 handles the displacement range, and from the displacement range we will determine the allowables for B31.3. We now go to ASME B31.3 paragraph 319.2.3 to look at displacement stress ranges. This section covers the displacement stress range from the displacement stress strain we just studied, specifically temperature, as you see, highest or lowest temperature, and also greatest imposed movement, which remember was wind, sway, wave, and also settlement. Further, this paragraph reinforces our stress-strain diagram study with reference to allowed yielding. Recalling our study on the stress-strain diagram and the cycle and its repeatability, that is further supported here in paragraph 319.2.3 as shown. This repeatability of reversal and redistribution of the cycle ensures a safe design. ASME B31.3 installs a very important clause in this paragraph that actually carries through the software for piping stress, through concepts when you look at displacement stresses, and that is the stress-free state, defined here to be the installed condition. Let's discuss this by way of example. Let's say that you install a piping system at 70 degrees Fahrenheit on the Gulf Coast, and the system operates at 1,000 degrees. Then it's very clear that the stress range we're talking about here is from 70 degrees to 1,000 degrees Fahrenheit. But say we have some cold temperature on the Gulf Coast and the temperature drops in the winter to 10 degrees Fahrenheit. Is the displacement stress range then measured from 10 degrees Fahrenheit to 1,000 degrees Fahrenheit? That's the question. Well, let's look at that. As it goes from 70 to 10, there would be a contraction. When it heated back up, then you would have that redistribution of stress to 70 degrees, a zero stress state, and then you would have the other stress range from 70 to 1,000 degrees Fahrenheit. So you have two stress ranges with this example. So far, for displacement stress range discussion, we have looked at thermal and imposed loading. But what about sustained? Well, we showed that sustained had its own displacement, which is not included in this discussion. But what happens if the thermal displacement redistributes the sustained loading of the pipe? Let's look at that. As you can see, as the pipe heats up, the support at the top lifts off and adversely loads with sustained weight the lower support. As such, the additional strain on the lower support would be included in this displacement stress range since it is because of thermal, and it will become part of the computed displacement stress range, S sub E, usually calculated by the pipe stress software. Now that we've covered stress-strain displacements, we want to review this portion of the video before we go into determination of displacement stress-strain limits per ASME B31.3. First, we learn that there are two types of displacement: self-limiting and sustained. We also recognize that displacement strains produce displacement stresses. We identified self-limiting displacement stresses as being predominantly thermal stresses in the code. Next, with our work with the stress-strain diagram, we saw that sustained stresses can never exceed yield. But self-limiting displacement stresses can exceed yield from the stress-strain diagram work that we did. We also discovered a very important characteristics for code-compliant displacement stresses, and that is that they follow a repeatable cycle when loaded, unloaded, and reloaded. This repeatability is the basis for it being code-compliant because it is predictable and behaves when it is within the limits established by the code. We also saw where, in many cases, thermal stresses and sustained stresses are not necessarily independent, and that thermal strains and displacements can unload sustained supports and thus must be considered. We also saw that where sustained stress displacements always start from zero, no load, and progress to a load stress state. As such, since anything minus zero is just anything, sustained stress limits are a fixed value. However, the same cannot be said for thermal, self-limiting displacement stresses and strains because they occur over a temperature range. They're not fixed in any way for any given project. Thus, the limits refer to a range of stresses in B31.3. And because thermal displacement stresses and strains are over this range, there is normally associated with such a range a reference temperature. And the state that we're talking about as far as the range from the reference temperature can go either up or down or even both from the reference temperature. The reference temperature we speak of is normally the as installed state or temperature when it was being constructed. Thus, since the thermal displacement stresses and strains occur for a given design over a range, then B31.3 stress limits that cover that are a range as well. This completes our study of displacement stress strain for B31.3. Displacement stress strain is foundational to ASME B31.3 for the subject matter expert, and thus I would recommend that you copy this screen and you study it because it's very likely to be strongly present in exams and quizzes that follow this video and at the end of the course. We now move to our next video, which will be limits of calculated stress. See you there.